Okay, so thank you all for staying until the end. And I guess on behalf of everyone, I want to thank the organizers for organizing this great conference. Thanks to the organizers. And so I don't know if my talk is going to go beyond Riemann or below Riemann, but it will be pseudo-Riemann. And more precisely, I want to explain correspondence between two kinds of pseudo-Riemannian locally symmetric spaces. On one side, I will have what I will call ADS quasi-Fuchsian manifolds. Of dimension quasi-Fuchsian manifolds of odd dimension 2D plus 1. And on the other side of this correspondence, I will have compact quotients or compact Clifford-Klein forms of these particular pseudo-Riemannian symmetric spaces, which will be the homogeneous space O2D2 mod UD1. So this group is the orthogonal group of a quadratic form of signature 2D2. And this is the subgroup preserving a compatible complex structure. And this correspondence, so the goal of the talk will be to detail this, but let's not be too mysterious. So here on this side, these quasi-Fuchsian ADS manifolds are some, slightly stronger thing than, but essentially globally hyperbolic maximal Cauchy compact manifolds. So they have the form M equals omega mod gamma with omega, a subset, an open subset of the anti-de Sitter space of dimension 2D plus 1, and gamma, a subgroup of the isometry group of ADS, which is precisely O2D, 2. And the correspondence here is that the same group gamma will give you a compact quotient N equals O2D 2 mod U D1 mod gamma. So there are two directions to this bijective correspondence. This direction has been known for some time, at least from Van Nicassel thesis, but I will present a new and more concrete explanation of this map, which is a joint work with Daniel Moncler and Jean-Marc Schlenker. And the other direction is the particular case of a joint work which is in progress with Van Nicassel. Okay, so the plan of the talk is first talk about globally hyperbolic ADS manifold, then talk about compact Clifford-Klein forms, and then explain how the correspondence works. So one, globally hyperbolic, maximal Cauchy compact ADS manifold. So let me introduce them. I should say also that this correspondence, everything is very well understood for D equals 1. So for ADS 3, and these objects are understood by MES. But the correspondence, I don't think it works exactly the same for D equals 1. So in all the talk, you should think of higher dimension. So D is at least 2. Okay. So what's a globally hyperbolic ADS manifold? First, it's a manifold locally modeled on the anti-de Sitter space. And so let me recall a definition. So ADS 2D plus 1, it's the Lorentzian analog of the hyperbolic space. So you look at a vector space of dimension 2D plus 2. On this vector space, you put a quadratic form of signature 2D, 2. I'm doing everything in so odd dimension because of the correspondence, but in this part, what I'm saying works for any dimension. You take a quadratic form of signature 2D, 2. And you look at the vectors, the quadric, where this quadratic form is -1. And so it's homogeneous under the action of the orthogonal group of the quadratic form. And the isotropy subgroup, the group fixing a point, is the group fixing the orthogonal, preserving the orthogonal. And so it's O 2D1 times O1. Okay, so this is our anti-de Sitter space. And if you restrict the quadratic form to the tangent space to ADS, you get a Lorentzian metric. Of constant sectional curvature, -1. Okay, so now what is a globally hyperbolic Cauchy compact manifold? So GH is globally hyperbolic, C is for Cauchy compact, and M is for maximal. So GHC ADS manifold is a Lorentzian manifold of constant curvature. But if you don't want to think about curvature in the Lorentzian setting, it just means that it is locally isometric to anti-de Sitter space. And curvature -1. And then you have a topological condition, which is you want that M contains a hypersurface, which is compact with that boundary, space-like, meaning that the metric restricted to H is positive definite. And intersecting, we have this causality condition, intersecting every causal curve in a single point. Okay, but if you don't like, I mean, Lorentzian geometry, and fortunately, these objects have a very another very concrete description, which is essentially due to mass. But I think in higher dimension, it was written by Barbeau. So if you have, sorry, maybe I should say that it's, so this H is called the Cauchy hypersurface. Cauchy compact means that you assume that the Cauchy hypersurface is compact. Sorry? I mean, the theorem is, in my mind, gives a clearer picture of what these objects are. But the point is that it's a manifold locally modeled on IDS with a space-like surfaces that essentially sees everything. In particular, M is H times R. topologically. And what I wanted to, it's really locally, it's Lorentzian, the local geometry is the same as ADS. Sorry, it's an inclusion. Globally, hyperbolic, and C is for Cauchy compact. It's 1C for 2, maybe I should put C square. Okay. Cauchy compact means that, so globally hyperbolic, if you remove compact, if you want, and Cauchy compact is you assume that the Cauchy hypersurface is compact. And maximal, so the M in GH, MC, maximal is maximal for the inclusion of globally hyperbolic Cauchy compact space. Sending inclusion of pairs H. Even in the Cauchy compact case. Again, it doesn't really matter. So this theorem of Metz and Barbeau. So the point is that, in particular, it's an ADS manifold. So its universal cover, for instance, has a developing map to ADS space. And the theorem will tell you, for instance, that the image of this map is a convex subset of ADS, a convex open subset. So it says that if I have M, globally hyperbolic, maximal Cauchy compact, then M is of the form omega mod gamma, and H inside M is some H tilde mod gamma, where H tilde is something. So what is H tilde? Where, so H tilde is a complete space-like hypersurface in ADS 2D plus 1. Omega is what's called the domain of dependence of H tilde. So I won't give its precise definition. So it's some convex open neighborhood of H tilde. And gamma is a discrete subgroup of isometries, O2D2, preserving H tilde, omega, and acting properly, discontinuously, and co-compactly on H tilde. So that in the quotient, I do have yes, so the picture is really the following. So ADS, so I'm going to draw ADS 3 because it's really the only one that you can draw. ADS is something in a projective chart. It's the interior of a one-sheeted hyperboloid, okay? Horizontally like that, if you cut with a plane, you get a disk, which is really a hyperbolic disk, okay? A Cauchy hypersurface, it is somehow a deformation of a space-like hyperbolic disk. So what you will have is something like that, which is a space-like, so this is H tilde. It's a codimension 1 disk, space-like disk in ADS, okay? Then you have you have convex neighborhoods of H tilde, but you have one which is a preferred one, which is in some sense the maximal one. You have a convex neighborhood that looks something like that, omega. If you want, for instance, you can, it's the dual of the convex hull of H tilde, if you want, but it doesn't matter much. The point is that there is a canonical largest convex neighborhood and that's the one we take. And the point is that you have a group gamma, a group of isometries gamma, that acts properly discontinuously on H tilde, and it acts properly discontinuously on the neighborhood of H tilde, and omega is the largest one. And your manifold is the quotient of this domain by gamma, and it contains H tilde mod gamma, which is a space-like compact hypersurface. Sorry? So there is a. I'm not very good with relativity terminology, but yes, that somehow if you the boundary has a there are some uses the something called the initial and terminal singularity in the boundary. Yes, they are like the dual to so you have the convex core, the boundary of the convex core here, and here you have the dual of the boundary of the convex core and the initial singularity. No, you don't have to, because in fact, anyway, this domain omega is going to live inside one fundamental domain. It's going to live between one hyperplane and that's opposite hyperplane. No, ADS is as a pi1, which is Z, but so really the universal cover picture is that if you double this, what you see is like copies of infinitely many copies of this hypersurface, but the domain omega, in any case, they are something like that. And also, I'm taking the double cover of the projective model, but again, it doesn't matter much. You should really think, I mean, an equivalent definition of the groups that appear here are just groups of isometries acting properly discontinuously and co-compactly on a space-like hypersurface. And I call them quasi-Fuchsian because they are like in some sense, some generalization of and some anti-de Sitter generalization of quasi-Fuchsian manifolds where you have in H3, you have a group acting properly discontinuously and co-compactly on a nicely spreading disk. Okay, and so no, sorry, I went too fast because these, I don't want to call them, all of them quasi-Fuchsian. I want to add some condition to call them quasi-Fuchsian. And this condition is that, so there are, it's the union of various theorems, so that mainly theorem of Barbeau and the work of Danziger, Guerrito, Cassel. So if you have a globally hyperbolic Cauchy compact manifold, then you have a number of properties that are equivalent. In which order should I put it? So the first one is you can choose your Cauchy hypersurface to be convex. There exists H convex Cauchy hypersurface. An equivalent condition is that the group gamma is a Gromov hyperbolic. The third condition is that gamma acts convex co-compactly on omega in the following sense, in the sense that there exists C inside omega, a closed, non-empty convex subset and so gamma invariant gamma invariant and such that C mod gamma is compact. And the fourth property is that, so I don't want to discuss much the boundary at infinity, but there is, in the projective model, you have a boundary at infinity of ADS, which is a projectivization of isotropic lines. And H tilde, it extends to a sphere on the boundary. The boundary is the Einstein space, and this sphere is achronal. And the condition here is that the boundary of H tilde is acausal, so that it doesn't contain isotropic segment. And the fifth condition is that gamma as a discrete subgroup of O to D2 is P1 and Oz off. And again, I won't define or talk about P1 and Oz off, but it's exactly the definition that Johan gave. If you see O to D2 as a subgroup of SL 2D plus 2R. Okay? So you have all these equivalent characterizations of what I will call, so in this case, I will call omega mod gamma and gamma quasi-Fuchsian. In dimensions 2 plus 1, you have, I will give examples, but basically you have the mesh things. We give you quasi-Fuchsian things. And then there is the flat degenerate thing when you put Z2 as a lattice in O11 times O11 inside O22. And this one is global, gives you something which is globally hyperbolic, but not quasi-Fuchsian. Okay, so let me better that I erase with yes, I could. In fact, if it's convex, then it's negatively curved. So that's how you prove 1 implies 2. Okay, so now let me give you, to tell you a bit about examples of such things, because part of why the story is interesting is that we have, in fact, quite a lot of examples. And the first examples are what you will call the Fuchsian ones. So yeah, I'm sorry, I should probably have erased with the sponge, but so the Fuchsian example will be if you take gamma to be a uniform lattice, so I mean co-compact lattice in O2D2, 2D1, sorry, which is the isometry group of the hyperbolic space of dimension 2D, and you put O2D1 inside O2D2 as a stabilizer of a hyperplane. And in that case, what happens is that simply that so the Fuchsian case, in the Fuchsian case, you have this totally geodesic hyperbolic copy of the hyperbolic space, and you're acting co-compactly on this copy. And the domain of dependence, omega, you can draw it. It's this whole cylinder, but not very important. The point is that when you have a totally geodesic Cauchy hypersurface, this is an example. Okay, this is the first example, but there are more. And the first source of more diverse examples are deformations of Fuchsian, which justifies somehow the terminology quasi-Fuchsian. Okay? And so, in fact, but it's even better than in the quasi-Fuchsian, the traditional quasi-Fuchsian case. There is a theorem by Barbeau, essentially, that any continuous deformation of so if you have gamma inside O2D2, you look at the inclusion of gamma and you deform it continuously in the space of representations of gamma in O2D2, then every continuous deformation of this representation is quasi-Fuchsian. Sorry, if of I quasi-Fuchsian. So if you start with something which is quasi-Fuchsian and you deform it continuously, it is still quasi-Fuchsian. So whenever you have a quasi-Fuchsian group and it has a nice deformation space, then the whole deformation, the whole connected component in the character variety is quasi-Fuchsian. Where representation, quasi-Fuchsian representation means that it is discrete, faithful, and the image is a quasi-Fuchsian group. So in particular, if you start with a Fuchsian group and you deform it into O2D2, then you get something which is quasi-Fuchsian. And you can do such deformations. So deformations of Fuchsian representation exist, of Fuchsian groups exist. And it's essentially, well, it's essentially due to Johnson and Nilsson. They did deformation in the isometries of hyperbolic space of dimension one more, but the exact same argument works in ADS. The point is that you have hyperbolic manifolds that admit separating totally geodesic hypersurfaces, and then you have a bending deformation in a higher dimension. So this already gives a large family of quasi-Fuchsian ADS manifolds. And about 10 years ago, it was conjectured that all the examples were like that every quasi-Fuchsian was a deformation of a Fuchsian. But in fact, this is not true, and there are more examples. So there is a paper of Lee and Markey that constructs quasi-Fuchsian Coxeter groups. Which are not isomorphic to hyperbolic lattices. So they cannot be, in particular, they cannot be deformed to something Fuchsian. So this is in dimension between 4 plus 1 and 8 plus 1. They have examples. Can you read? Or? And with Daniel and Jean-Marc, we have exotic examples in every dimension. We prove that we have examples where H, the Cauchy hypersurface, is a so-called Gromov-Thurston manifold. And so this works for any dimension, at least 4. And so the Gromov-Thurston manifolds are some sort of ramified covers of hyperbolic manifolds, and they are known to be like negatively curved, but not isomorphic to hyperbolic lattices. but you can realize them as Cauchy hypersurfaces in ADS manifold. They are in dimension 4 and higher. And in fact, again, here I write 2D because I'm taking even on things that are even dimensional, but I mean, it's any dimension. Yeah, yes, you can have arbitrarily pinched curvature. Yes, because the group remains hyperbolic, in fact. The point that the limit set is, because it is achronal, I mean, it must remain Lipschitz, so even a sequence of representations that converge will still preserve a Lipschitz manifold. And this Lipschitz manifold will be, you prove that it will be acausal because the group gamma is still hyperbolic. That's roughly the proof. Okay. So this is what I wanted to say basically about these quasi-Fuchsian manifolds. ADS. Do you have questions? Yes, maybe. But then it will take, maybe this one is better. Let's try. Not tab erased. Okay, so let me go on with the second part, which is the right side of the correspondence. So compact quotients of homogeneous space, or sometimes called compact Clifford-Klein forms. But this is just a pedantic way of talking about the quotient of a homogeneous space by a discrete subgroup. So let me put a bit of a more general setting. Let's say that G is a semi-simple Lie group. H inside G, semi-simple or reductive, maybe say reductive subgroup. Then in this setting, the killing metric of G induces a G invariant pseudo-Riemannian metric on G mod H. So G mod H is a pseudo-Riemannian homogeneous space. I'm supposed to stop in. G mod H is pseudo-Riemannian homogeneous space, and a compact Clifford-Klein form or compact quotient is simply the space of the form G mod H mod gamma, where gamma included is a discrete subgroup of G acting properly, discontinuously, and co-compactly on the whole space G mod H. Okay, so now you have to be careful that when H is compact, this is the same as asking for gamma to be a uniform lattice in G. But when H is non-compact, uniform lattices will act ergodically. They are too big. And so when H is non-compact, so if you're in the pseudo-Riemannian setting, the question is whether these compact quotients exist, and understanding them is still very open, and it's somehow more subtle than the Riemannian setting. And in fact, lots of homogeneous spaces G mod H do not admit compact quotients. And also in the Riemann setting, you have a very strong rigidity theorems that tells you that basically all these compact quotients are actually rigid except for quotients of the hyperbolic plane. And in this pseudo-Riemannian setting, things are again very open, but there are more interesting examples. There are few but infinite families of such homogeneous spaces, which are known to admit non-rigid compact quotients. And I can give you the list. There are essentially 3 families. You have G, you can take G to be SON1 times SON1, and H, it's inside G is the diagonal embedding of SON1. So G mod H, you can see it as the group SON1, but with the action of SON1 times SON1 by left and right multiplication. You have the same thing with SUN1. You do not have the same thing with SPN1 because lattices in SPN1 are super rigid. And you have O to D2 mod U D1. So you could say, well, why consider this symmetric space? Why is it interesting? Well, it's one of the only families which are known to have compact quotients with a very nice deformation theory. Okay, so now I can state the 2 theorems giving the correspondence. So the first theorem is, I don't know who it should be attributed to. I'm putting Guerito, Guichard, Cassel-Winard because it's one of a crucial example of one of their work, but essentially I think it was remarked long ago, except that maybe the theory of quasi-Fuchsian ADS manifolds was not so well developed. And I will add something. So we give a new proof of this theorem. So the theorem is that if you have gamma in O to D2, which is ADS quasi-Fuchsian, then gamma acts properly discontinuously and co-compactly on O to D2 mod UD1. And this is exactly why you have such a nice compact quotients here with a good deformation theory, because you have all these ADS manifolds that give it to you. And so our theorem with Daniel and Jean-Marc adds something more. It explains the relation between these two things. And in particular, it describes completely the topology. It says that O to D2 mod U D1 mod gamma is a fiber bundle over the Cauchy hypersurface. And the fiber bundle with whose fibers are compact homogeneous subspaces of the form O2D mod UD. It's a O2D mod UD fiber bundle over the hypersurface H. Okay, and let me state the other theorem, which is the other direction of the correspondence. The other theorem says that if gamma inside O2D2 is acts properly discontinuously. I'm sorry that it's kind of obvious what I'm going to write, but if it acts properly discontinuously and co-compactly on O2D2 mod UD1, then in fact it acts properly discontinuously on a space-like complete hypersurface. Then gamma is ADS quasi-Fuchsian. Okay, so these are the main theorems, and they tell you that the groups that appear on both sides are exactly the same. And how much time do we have left? 6 minutes. So in 6 minutes, I think I want to talk about this theorem, because the point is that the original proof of Guerito, Guichard, Alcacer, Winart consists in saying that so these groups gamma that are quasi-Fuchsian, they are P1 and Ozoff, and the P1 and Ozoff property implies the Benoit-Kobayashi properness criterion. So it's directly a consequence that gamma acts properly discontinuously on O2D2 mod U D1 because of some property of the Cartan projections. And then by a cohomological dimension argument, the action must be co-compact because gamma has cohomological dimension 2D, and that's exactly what the cohomological dimension of a group acting co-compactly must be. But somehow this proof is a bit unsatisfying, is that it does not really explain the relation between these two spaces. And so in our paper, we prove this, but we prove more. We really explain how you can understand this relation. And the point is that, let's call it theorem A, B. So the point is that first you want to interpretate this weird homogeneous space, O2D2 mod U D1. You want to understand what it means in terms of the ADS geometry, right? And there is the following lemma, which is that, so maybe, no, let's take a bit of time. Okay, so let me first define, so a killing field on ADS. So it's a vector field that infinitesimally preserves the metric. But more concretely, it's really the vector field associated to So it's a vector field XU on ADS associated to an element U in the Lie algebra of S of O2D2. So associated to U inside SO2D2. I'm giving them two different names, but you could say that really the Lie algebra of SO2D2 is a Lie algebra of vector fields on ADS. And this is what you call the killing field, okay? And I will say that XU is unit time-like if, if the Lorentzian norm of XU is -1. So it's pointing in a time-like direction, and it's constant equal to -1. Okay, and the lemma is that XU, you take any U in SO2D2. This is the Lie algebra, right? XU is unit time-like if and only if U squared, you see U as a matrix of size 2D plus 2, a square matrix of size 2D plus U, if and only if U squared equals minus the identity. But this relation means that U is a complex structure on R2D2 compatible with the metric. And so in fact, the space of unit time-like killing fields it's the space of complex structures compatible with the quadratic form. And so it's homogeneous under the action of O2D2. And the isotropy subgroup is UD1. So this is the first thing to understand. What is this space relatively to anti-de Sitter geometry? It's the space of unit time-like killing fields. And now comes the lemma. The main second lemma, main lemma. Assume that now in ADS, you have this hypersurface H tilde, which is in ADS 2D plus 1, which is complete, space-like, and strongly convex, meaning that the Hessian is a positive definite at every point. It's really like a differential geometry lemma. Then any unit time-like killing field XU is orthogonal to H tilde, at a signal point. I'm not going to prove this, but I mean, the heuristic, the idea is somehow that a killing field cannot really be orthogonal to a convex hypersurface at two different points, because when you push along this killing field, on the one hand, you're supposed to preserve the matrix, so you're supposed to preserve the length. But on the other hand, you're pushing a convex hypersurface towards its normal. And this tends to, in hyperbolic geometry, this would tend to increase the length. In ADS geometry, it tends to decrease the length. But so this is sort of the contradiction. And so this defines a projection from O to D2 mod U D1 to H tilde. And this projection is gamma equivariant if H tilde is gamma invariant. And the fibers of these projections, the fiber of this projection, you can verify that it's O2D mod UD. And so it's compact subspace. So this is a proper map to H tilde, which is gamma equivariant. And because gamma acts properly discontinuously and co-compactly on H tilde, it acts properly discontinuously and co-compactly on this homogeneous space. And so I will stop here. Thank you.